Alright, so today we're looking at limits at infinity. So basically that just means that instead of x approaching a number, we're approaching infinity now, which we did a couple of those with the graphs yesterday, right? So now you just don't really have graphs. So super easy if you do have a graph, and there are a few problems where we'll look at the graph. But yeah, so for the first ones, if you have 1 over x, you've got to visualize that in your head. So that's one of our parent functions, and you should know what that looks like, yeah? So what does the graph of 1 over x look like? I think Alex was trying to draw it back there. It's this one, right? That's 1 over x. So as x approaches infinity, what is y approaching? 0. And as x approaches negative infinity, what is y also approaching? 0. So basically, you have this rule down here, which is great, but do y'all remember Bobo Bottom eats DC? Do y'all remember that, how we use that for your horizontal asymptotes at the beginning of the year? Well, if you do, awesome. If you don't, that's basically what we're applying today. So if it's bigger on bottom, if your exponents are bigger on bottom, you're going to have a horizontal asymptote at 0, which just means you're going to approach 0 from positive or negative infinity for your limits. Does that make sense? So that's the Bobo part. Bottom, it means if it's bigger on top, there's not a horizontal asymptote. So like we did synthetic division or long division to find your asymptotes there. But today, that just means it's going to go to infinity if it's bigger on top. So as x approaches infinity or negative infinity, it'll go to infinity or negative infinity. And then the each DC part means the exponents are the same, so you divide your coefficients, which would be like what we're going to do for this one right here. So as x approaches infinity, your exponents are the same, right? Your highest exponents. So divide your coefficients, 3 divided by 5, that's what we would approach. Is that all right? So it's that easy, guys. That's all there is to it. Questions right now? Alright, so for the next one down here, we've got the limit as x approaches negative infinity for each of the x. So you've got to know what that graph looks like in your head so that you could like know what your limit's approaching. So if you've got each of the x, that's just like an exponential function, right? So what is your graph going to look like for that? Right? Really big, really fast? So it's going to look something like this. So as x approaches negative infinity, what is y approaching? Flattening out towards 0, right? Is that okay? Alright, so for the next one, we've got the limit as x approaches infinity of sine of x. So again, you gotta know what that graph looks like. So what does your sine graph look like? Right? It just oscillates. And do y'all remember what we say when you have a graph that oscillates? What about our limit? D&E. Is that alright? Questions? Alright, so that's all the practice that we have on those. So if you're given a problem and you can't remember like your rules or whatever, or you don't remember what the graph looks like, for y'all, for this class, you're going to have your calculator on the exam to just graph it and see where it's going to. Does that make sense? So you can just look at the graph and find it that way, because I think we're good at finding the limits from the graph, right? Or like pretty good with it. Right. So yeah, that's what I would recommend you do if you forget or don't know what the graph looks like. So the bottom section, we're going to start taking limits of sequences, so like we were doing earlier this week, but now we're taking the limits of those. So just remember that it's convergent if it goes to the same number, and it's divergent if it doesn't, so if it like oscillates or something like that. So you can look at the graphs for these again to see if it's convergent or divergent. Do y'all remember for your geometric sequences how we can tell if it's convergent or divergent? Your r is less than 1, right? So that's not always going to be helpful for these. So that's where I think that looking at the graph is going to be the best thing for y'all. So for the first one here, we don't even have to look at the graph, because if you are looking at your function, we've got n over n plus 1 as n approaches infinity. So your exponents are the same. So what do? Divide your coefficients. So 1 divided by 1 gives you 1. Is that okay? Questions? That's it. All right, so the next one over there, we got to decide if it converges or diverges. So I think it's helpful to like list out the sequence because we don't have it. So if we do that, then we can see what's going on. So if you have -1 to the first power, what do you get? -1. Then what if you have -1 to the second power? -1 to the third power. -1 to the fourth power. What's happening? It does what? Goes back and forth. It oscillates, right? So is it convergent or divergent? Divergent. Because it oscillates, because it goes back and forth. It's not approaching one number, it's just bouncing back and forth. I'm sorry? So for the last part here, we want to find the limit of this sequence. So we're going to go ahead and set that up. So we're going to do the limit as n approaches 0 of 15 n cubed and inside. So if we're looking at this right now, what's like our first instinct? It should be infinity. I just forgot to draw infinity. I should put a 0, make that infinity. Yeah, because it's the limit of a sequence. So anytime you're doing the limit of a sequence, it's always going to approach infinity. So I don't know about y'all, but if I'm looking at this, like, I think we need to start multiplying stuff out in your numerator, right? That's not going to be helpful, so don't do that here. Do I remember yesterday some of those rules that we had that say you can like pull constants out of the limits? Is at the top of the notes from yesterday. I don't know if everybody has those. You could grab and pull out real quick. But it was just like if you had the limit as x approaches a of c of f of x is c times the limit. That was one of them. That's what we were talking about. Or what I'm talking about where c is some constant. So if you have a constant times your function, you can just pull the constant out. So that's what we're going to do here. So we could pull out the 15, and you could also pull out the 6, right? So we're going to pull out a 15 over 6. Huh? We're going to move that down here because it's all being multiplied. So I don't know why they set it up like this. It's probably something to do with like where the sequence comes from, but essentially you'll just pull out this number, and move your and whatever over here every time for one case. And then we got n cubed on the bottom. Is that okay? So we just pulled out the 15 over 6. Questions so far? So from there, we could multiply out all this stuff in the numerator, but it's not really necessary because we just need your leading coefficient or your leading exponent, right? To decide if we do Bobo button or HDC, Bobo button, HDC, right? So n times n is going to be what? Times 2n? 2n cubed, right? So n cubed on top and n cubed on the bottom. So what do? Divide your coefficient, so 2 over 1. Right, so this whole thing is going to be 15 over 6, which that reduces to 5 over 2 times, we said that was going to be 2 over 1. We need to do the HDC part. So then your 2's cancel and the whole thing just goes to 5. Questions on that? Okay. Are we all right? Okay, cool. So that's what we got today. Yep.